Okay. Hello, everyone. My name is Amnon Ptashek, and I'm from the Allotrope product team. We're going to go through a deep dive into modeling all the way to validation. We will discuss the interoperability of an ADF and an ADM. But to set the ground level, we will start with, just a moment, we will start with the W3C RDF Primer just to set the ground level. Let's start. The RDF, the Resource Description Framework, is a framework for expressing knowledge about resources. Resources can be anything. It can be equipment, it can be people, it can be devices, physical object, abstract concept, and we can visualize knowledge as a connected graph consistent of nodes and arcs. RDF statements expresses a relationship between two resources. A statement always has the following structure called triples: subject, predicate, object. Very simple. The subject and the object represent the two resources being related. The predicate represents the nature of the relationship. Usually the relationship is phrased in a directional way from subject to object and is called in RDF property. So in this example, Bob is interested in the Mona Lisa. Subject, predicate, object. Bob is the subject, Mona Lisa is the object, and is predicating Mona Lisa is interested in the Mona Lisa. The ability to have the same resource be in the object on one position, in one triple, and the subject in the position of another triple makes it possible to connect between triples, which makes it very powerful, makes the RDF very powerful. In this example, Bob has several properties, and the Mona Lisa has several properties. We are making the connection between the two by saying Bob is interested in the Mona Lisa, and we can infer that Bob is interested in something that was created by Leonardo da Vinci. IRI, which we'll present also later on, the International Resource Identifier, are used to identify resource uniquely. They can be literal. For in this example, Bob's birthday is July 4th, 1990. IRI are typically used in combination with RDF vocabulary that provides semantic context about these resources. In this example, we're using the universal RDF vocabulary such as friend of a friend. So we are using it in the case of Bob for three properties. We're using it, Bob is friend of a friend knows Alice. Bob is a type of person, friend of a friend, vocabulary person. And Bob, topic of interest is the Mona Lisa. It's actually mapping between the namespace of friend of a friend and the prefix FOAF and the ID in the vocabulary. RDF graph can be serialized using Turtle RDF triple language syntax. The Turtle syntax is human readable. So in this example, we see the Turtle syntax for the graph on the right side. So for example, subject, predicate, object, we have the Mona Lisa under the Wikidata namespace with the ID of Q12418, Mona Lisa. The creator, predicate, is Leonardo da Vinci. Very simple, very human readable. With SHACL protocol and RDF query language, we can query an RDF graph. For example, we can query for the people that are interested in the Mona Lisa. The query can be done for multiple triple patterns. In this example, we have a SHACL query, which is very similar to SQL. Select name, where name is a type of person, Bob is a type of person, and the topic of interest is the Mona Lisa. Now that we are expert already on RDF, we can dive into the modeling all the way to validation and discuss interoperability of ADF and ADM. Let's go. A generic ADF file has the following components. It has a data description, data cube, data package, graph store, audit trail that can be used for compliance feature, checksum, and the ADF file uses HDF5 as the underlying file format. The graph store is used to store user-defined graphs. It stores it in a form of RDF graph. The data description stores metadata about the file content. It stores it in a form of RDF graph in the graph store. The data description may contain contextual metadata about the data cube or the data package, or both of them. Specifically for the lab environment, it can describe results, sample, process, method, instrument description, and so on. The data cube contains multi-dimensional array of data. Specifically for the lab environment, it may contain measurement, result of an experiment, or process data. Data cube context, the metadata, is described within the data description. Similarly, we have the data package, but the data package is for general purpose virtual file storage system. We can optionally archive the same data that is in the data cube, but it's in original native raw format, such as Excel, PDF, Word, whatever the data came in a native format, and we can archive it in the data package. The data package context, the metadata, is described in the data description, and it can ensure data consistency and integrity. So now back to the IRI. The IRI, the International Resource Identifier, is a way to uniquely and ambiguously identify particular resources. We're using namespace to map prefix to IRI, allowing human-readable format, and ensure that a given set of objects have a unique identifiable name. In this example, and we'll use the example of equipment serial number across this presentation. So we are using the namespace of Allotrope Ontology result and the unique ID AFR 000119. Remember this number, 000119. So mapping between the namespace and the prefix AF-R, we get the equipment serial number in a readable format AF-R AFR 000119. And we can get the description of this identifier on the Perl server. The Perl, which is a persistent URL service that redirects requests to the proper web location regardless of the ever-changing web infrastructure. So we have a snapshot of the Perl description of the equipment serial number. The pattern of Allotrope identifier has the namespace, followed by the domain and 7-digit number. The domain is an uppercase abbreviation, so for the prefix of AFR, which is the namespace of Ontologies result, we have capital letters AFR, followed by 7 digits, 000119. So we have several prefixes that are mapped to different namespaces, such as AF-E for equipment, FN for function, M for material, and so on and so on. How do we get those unique IDs? We are minting IRIs. We have a tool for generating unique domain ID, and we'll see the tool later on. An IRI, once is minted, it should be unique and can never be changed. So now that we have our terms, let's organize our terminology. Entities within the vocabulary are uniquely identified, as we said, by a standard IRI. We have, in this example, we have 3 identifiers: the device identifier, the equipment serial number, the balance identifier, 3 IRIs, 3 terms. Let's organize them in our taxonomy. The taxonomy is an hierarchical classification of terms that describe a domain. In this case, we see that the equipment serial number and the balance identifier are subclasses of the device identifier. And if we use the Protege tool to see the taxonomy tree, we can see that the balance identifier and the equipment serial number are subclasses of the device identifier. So now that we have the taxonomy, we can start giving relationship between the terms. An ontology is a logic model that captures a domain in a computer understandable way, including entities, relations, and logic that controls relations. So in this case, we see the 2 resources. One resource is located in another resource, and another resource as part in another resource. And ontologies provide an unconstrained vocabulary that we can use to describe things, instances in our open world and give them a meaning, meaning what it is. Between taxonomies, we can have a relationship. From the graph, we can learn a specific equipment has contextual role in a process. How do we know that it has contextual role in a process? If we look at the ID 0002731 and we go into our Perl server, we can see that it has contextual role in a process. So an application can issue a query, retrieve a list of equipment ID, serial number that took part in a certain process. This is the relationship. To summarize, the Allotrope taxonomies and ontology addresses the laboratory analytical processes. The AFT formalized the hierarchical relationship of terms. The AFO is an ontology suite that provides a standard vocabulary and semantic model representation. So what is this model representation? Let's dive in. A model actually represents a use case. The model uses RDF graph to describe the use case. Again, a model uses an RDF graph to describe a use case. In the case of Allotrope, a standardized model for the pharmaceutical lab is called ADM, Allotrope Data Model. So Allotrope Data Model is a model. So if we standardize the ADM, we will get interoperability, which means heterogeneous vendor system can seamlessly exchange ADF files, read, write, process its data that adheres to the associated standardized ADM, which means different vendors with different instruments, if they will adhere to the standardized ADM, they can interoperate with and share ADF files and the data content. So how do we standardize an ADM? Let's go in. An ADM data instance contains an import reference to a manifest. And let's look carefully. This is an ADM model, but it's an ADM model data instance. That's why we have the disk in the sleeve. It imports the manifest. And the manifest, in turn, imports the SHACL that we will discuss in a moment, and the vocabulary. ADF file claimed to meet the use case if its ADM data instance passes the constraint within the SHACL shape, within the shape file, which we'll discuss in a moment. And this shape is referenced by the manifest. Again, let's take a careful look. We have the ADF file, we have the ADM data instance that reference through import the manifest file, and the manifest file reference through import the SHACL, the shape file, and the vocabulary. So again, the manifest maps the use case, which is the model, to the associated shape and the vocabulary. The manifest contains import references to the shape and to the vocabulary. So let's take a deeper look into the manifest. This is a manifest file described in an RDF using Turtle syntax. This is the entire manifest file, and it is very simple. We have three triples. We have the triple that states this is a manifest file. The next set of triple says that the manifest file imports two files. The conductivity shape, and this is a manifest for the conductivity measurement, and the merge TTL. What are those two files? One of them is the shape file, and one of them is the vocabulary. The conductivity shapes is the shape file, and the merge is the vocabulary. We can see the same thing if we are using RDF graph. We have the manifest, which import the conductivity shape, the shape file, and imports the vocabulary, which is the merge TTL total file. So what is this shape file? The shape file contains a set of conditions, and it uses SHACL syntax, shape constraint language, to describe those conditions. So let's dive into an example of a single condition. And again, we'll go through in the equipment serial number. So this is a single shape. And this single shape set a condition that the equipment serial number must have exactly one value of type string. Why is it one value? Because we have the cardinality, the minimum cardinality of 1, the maximum cardinality of 1, which means exactly 1. And the data type is a string. And we have here the definition for in the Perl server of has value, 000690. So we see that this is a constraint that is set on the property of the equipment serial number. When we dive into the shapefile, we have plenty of conditions. And this is just a screenshot of part of the shapefile in turtle format. Where when we will model a tabular table, we will have a set of conditions for each row in our table. For example, the measurement ID, we can see that the measurement ID must have an exactly one value of type string. Again, the maximum cardinality of 1, minimum cardinality of 1, which means exactly 1. Or the pref label. The pref label, the maximum cardinality is 1, the minimum cardinality is 0, which means we can avoid a pref label, a preferred label, if we want. And it states that the measurement time, we must have a measurement time present. And we are using in the shape a SHACL query to retrieve the measurement time. So how do we create and how do we produce the ADM data file? Again, the ADM data file, the data instance, represent an instance of the Allotrope standardized use case. In the modeling process, we use a user-friendly conversion tool to RDF graph. We have a tabular to RDF graph tool, we have aggregation to RDF graph, and we have a CMAP to RDF graph that we will dive in a moment. We add the sample data, and it references the tool, the manifest, using imports, or more precisely, all import. So the tool imports the manifest, which in turn imports the SHACL and the vocabulary. And we are using user-friendly tools to build the model by the SME, the subject matter expert. So let's dive into the tabular model. The tabular model is a set of key value pairs. It's a table. Keys can be clearly distinguished without any ambiguity, and no reference are required between keys, which means they can be standalone and accurately describe the data without relating to anything else. Keys are terms, IRIs, in the ontology, which provides a bridge to the semantic usage. The key value pairs context is represented only by the ADF they are defined in, meaning you can't have the keys in different ADF files. This is why it's so simple. It's just a table. And there may be no central node which connects the different keys. So in this example, we have a table with all the pref label and the IRI and the data type. So let's dive into the Excel spreadsheet that we are using for the tabular model to simplify the modeling process. This is the spreadsheet of the conductivity measurement model. It's an Excel file, and we see the different columns. The first column is the parameter type, whether it's a metadata or result data. Then we have the parameters such as measurement ID, run date, operator, machine ID, and the pref label, the preferred label. In our example that we are using the equipment serial number, the pref label for machine ID is equipment serial number. And we have our friend, the IRI, the 000119, that is the identifier for the equipment serial number. We have a column whether the parameter is required or no. We have the unit of measure. We have an example of parameter value. We actually plug in the the parameter value. In this example, serial number XYZ. For temperature, for example, we have 28.6, the unit symbol, degree Celsius, and the URI identifies the unit parameter. Now that we are going through the modeling, we're using the Excel spreadsheet to plug it into our Tabular to RDF conversion tool. The conversion tool imports the manifest file, if you remember, the manifest file, which in turn imports the shape and the vocabulary. And the Tabular to RDF tool output the ADM data instance. And we see this in total format. And if we take a closer look, we see the import here, the import of the conductivity manifest. And we see that each line of the Excel spreadsheet has a line in a triple in the total format. If we want to see it a little bit closer, we'll go again through the equipment serial number with the IRI and the string and the serial number value of XYZ. So zooming into the data instance, we can see the result AFR 000119, which is a preferred label with equipment serial number, and the value serial number XYZ, which is a string. Seeing the same information, but instead of in total format, just as an RDF graph, we can see our all import, the importing the manifest file, the ontology importing the conductivity.manifest, and we see the one-to-one triples for each line in the Excel spreadsheet. So we see our friend, the equipment serial number XYZ, and the temperature, for example, 28.6 degrees Celsius. Now that we have the ADM data instance, we have the model, we can generate an ADF file for the conductivity measurement.adf file. Similarly, the same process we apply for modeling a graph, but with different tool. Graph is a very powerful way to describe unstructured data and relationships. The modeling domain, where we're using graph, have multiple business objects and are much more complex relationships. A connected graph models the different relationships within our domain. And for modeling a graph, we're using the CMAP tool. With the CMAP tool, knowledge is represented and organized as concept map. And we see a partial map of the LCUV model CMAP file. Using the same process, we have a CMAP to RDF tool. We have the input, the CMAP, the input, which is the output of the concept map tool, inputting into our CMAP to RDF converter. We are importing the manifest file, which in turn import the shape and the vocabulary. And we are outputting the ADM data instance. And just to have a closer look into a single triple, for example, the electronic absorbance measurements, we can see the same thing. This was in a total format, and we can see it also in a graph RDF format, where we see it as a node with many relationships, many properties. Now that we have generated the ADM data instance, we need to validate it. We go into validation. And for this, we have the SHACL validator. The SHACL validator evaluates conformance of an ADM data instance with a set of conditions which in the associated shape file. If you remember, the ADM data instance reference the manifest, which in turn reference to import the shape file with all the set of conditions. So our SHACL validator has a plugin input for the data instance, for the SHACL shape, and for the vocabulary. And the output is a report whether it passes validation or it fails. And let's do an exercise again with our serial number. We will plug in the shape file with the cardinality of maximum cardinality of 1, minimum cardinality of 1, which means exactly 1 for the equipment serial number. And we'll plug in a data instance file with, we will violate it, and we will use two serial numbers. One serial number is XYZ, and the other serial number is ABC. We will pass it through the validator, and we'll get a false result. Conforms is false, and the result severity is violation. Why? Maximum count constraints component, which means we violated the maximum number of serial numbers. Let's fix it. We will fix it. We will erase one of the serial numbers, and we will have a single serial number. We will pass it through the SHACL validator, and this time we will get conforms true. We passed our validator. Last but not least, we have the ADF library, which is an application programmable interface written in Java and C# with extensive API to the different ADF components for the data cube, data package, data descriptor, and the rest of the component. Thank you very much for your attention.